Alright guys, pull out your notes and title this Roots. So let's go over a little bit of vocab. Roots are the zeros of a polynomial. Sometimes we call them solutions. They're also known as the x-intercepts, if you want to put that. Okay? Alright, so as you can see from the graph, we can find those roots by finding the x-intercepts. Remember we talked about a little bit about multiplicity, so notice it when it bounces right here, it's bouncing off the x-intercept. You know that it'll have multiplicity 2. So this one has 1, 2, 3, 4 roots. 1, 2, 3, because it bounces 4 roots. Rational, so we're going to find rational roots. So I want to go over rational a little bit. Rational is something that can be written as a fraction. So we're going to go through this go through this list. -5 is rational. -5/1. 3, also rational. 0.75, also rational. 3/4. Pi, irrational. Root 16, 4, rational. Root 5, not rational, irrational. And then 87/6, of course, rational. So our job, we're going to talk about rational roots and find all roots, but you're going to need to know this word rational roots. Okay, so another thing about roots besides rational is we also have real roots, and rational are part of the real root system, but we also have imaginary roots. So remember, real roots will be, like we said earlier, this one has 1, 2, 3, 4 rational roots, maybe irrational, but they're all real. Imaginary, okay, this has 2 real roots and then some imaginary. This has all imaginary roots because there's no x-intercepts. Alright, what if I had a polynomial of degree 4, but we could only see 2 x-intercepts when we graph it? What would we know about the other roots? Well, we'd know that they are imaginary. Remember, imaginary come in conjugate pairs, as we talked about earlier. So if you have 3i, you know you're going to have negative 3i. If you have 4 minus 5i, you're going to have 4 plus 5i. Remember that conjugate. So imaginary root always come in pairs. Irrational roots always come in pairs as well. Alright, so we're going to throw it back a little bit to last year's stuff. So if I ask you to find the solutions or find the roots of the polynomial, specifically this quadratic right here, think about the strategies you used last year. You had factoring, you had quadratic formula, completing the square, but if you remember, we can't just get x alone. We can't minus 20 and there's not like terms. The x squared and x are not like terms. So what we had to do is factor. So I'm going to factor this one pretty quickly. Once we factor, we can use the zero product property to set each one equal to 0 and then solve. And we were able to find those roots pretty easily last year once you learn these techniques. Okay, but what if it's a little bit harder to see? What if you cannot find the roots by factoring? I don't know how to factor this, right? But that's what we're going to learn today real quick. So, degree 7, I know that there's 7 roots. Some might be irrational, some might be imaginary, some might be rational. Probably mostly real, but yikes, I don't have the skills to factor this. Okay, so that's what I'm here today for, to teach you how to factor that. So we're going to use this rational root theorem. So if you remember, when you factored last year, you really focused on the a value and the c value. And last year you multiplied those together, right? So 1 times 20, and then you made a list of factors of 20. Right, so you made a list of the possible numbers that could work to break up that b term. But then we just found, so what multiplies to give us 20 but adds to give us 9, we could kind of narrow it down. So what we're going to do today is similar, but a teeny bit different, okay? So we're going to factor this. It's not going to be as quick. You got to have a little bit of patience for this, but we can do it. So the rational root theorem says if you take the factors of the constant at the end and the factors of the leading coefficient and divide every factor of the constant by every factor of the leading coefficient, you'll have the list of possible rational roots. Just like last year, you made a list. Our list's a little bit different, but just like last year, you made a list and were able to narrow it down. Same idea, we're going to make a list. So to help us remember everything, we call it P and we call it Q. Now remember, it's always back to back. You cannot go belly to belly. If you go belly to belly, you know you have it wrong. Belly of the letter. Okay, so P and Q, I need to identify those numbers. So I'm going to list all the factors of P. So I have 1, 5, but I also have -1 and -5. Okay, so don't forget that. And then the factors of Q, I'm going to get 1 and 2, and then -1 and -2. All right, so then we have to take every factor of P and divide it by every factor of Q. So the list is pretty long. All right, so I'm going to start with this 1, and I'm going to divide it by all 4 numbers. So 1 divided by 1 is 1. 1 divided by -1 is -1. Sorry, I'm jumping around. 1 divided by 1 is 1. 1 divided by -1 is -1. 1 divided by 2 is 1/2. 1 divided by -2 is -1/2. All right, so if you notice, for every positive rational, we will have a negative. So what some people actually do is they don't even list the negatives. It just makes your list a little bit shorter. So then they say, all right, I'm going to take this 1, I'm going to divide it by 1, and then I'm going to divide it by 2. So take the P, divide it by the Q, and then they just put plus minus 1. So from here on out, I'm going to just ignore positive or negative because I know that every positive factor can have, right? -1 times -5 also creates that. So I know that for every positive, there will be a negative. All right, so I'm done with the 1. I divided that P by every Q. Now I'm going to take this 5 and divide it by 1, which is 5, and divide it by 5/2, which is that. Okay? So I have 1, 2, 3, 4, 5, 6, 7, 8 possible rational roots. If we look at the degree, we know that there's only 3 possible roots. They might not all be rational, but there they are. Okay? All right, so this is how you make your list of possibilities. Now, how do you know which ones work? Well, if you remember, we learned about the remainder theorem. The remainder theorem says if you plug in a 0 or a root or an x-intercept, right? If you plug in one of these values from the list and you get an output of 0, so we input it in the polynomial. If you get an output of 0, you know that it's part of the factor. It is a solution. It is a root. So I'm going to use the remainder theorem. So I'm going to do 2, and I'm just going to start with 1. 2 times 1 cubed minus 1 squared plus 2 times 1 plus 5 equals, well, hopefully it equals 0, because if it equals 0, then we know that it is a factor. Well, it's a root, but we can change it into a factor. All right, 1 cubed is 1, so that's 1 times 2 is 2, minus 1, plus 2, plus 5. That is not 0. I don't know why I keep writing 0, sorry. So 2 plus 2 is 4, minus 1 is 3, 3 plus 5 is 8. So I know that positive 1 won't work. So I'm going to now try -1. So I'm just going to change all those to negatives. I'm going to plug in a -1 and see if that works. So -1 cubed is -1. -1 times 2 is -2. All right, -1 squared is 1, but minus 1. 2 times -1 is -2 plus 5. So I have -2 minus 1 is -3, minus 2 is -5, plus 5 is 0. So I know -1, so I'm going to write actual roots. I know that -1 is an actual root. Now remember, I have 2 more that I'm potentially looking for. So let's do it again. So instead of -1 now, I'm going to move on in my list to, I guess, I'm going to skip the 1/2. We'll come back to that. Let's do 5. All right. So 5 cubed is 125. 125 times 2 is 250, right? Minus 25 plus 10 plus 5. So I don't think that's going to get us there. 250 minus 25 is 225. 220, yeah, 220. So the remainder, if we would have tried to divide it, the remainder is going to be really big. 5's not going to work, right? All right. So then I'm going to keep going down my list. But as you can tell, this is kind of tedious. So we're going to stop right there. But you would want to check all those. I will show you a shortcut in a second, but that's the general idea. So this is the rational, oops, as I erase everything. This is the rational root theorem. You find the factors of p, which is the constant, factors of q, which is the leading coefficient, and make sure that you divide every p by every q. So remember, in the alphabet, p comes before q, so p's in the numerator. P divided by q, every factor of p divided by every factor of q. Then you can use the remainder theorem to go through and see which ones are actual roots. All right, so let's do this one again. So write this down and then try it. So remember, I can't factor this, okay? You can try factor by grouping. It's just not going to work, okay? Sometimes factor by grouping will work, but I can look at the numbers and tell you, not going to happen. So I use the rational root theorem, which says take the factors of p, take the factors of q. You're going to divide those out. You're going to find a nice list. Now remember, I don't worry about the positives or negatives because I know that -2 times 2 is 4, but that's a bad example. So -1 times 4 is -4, but also -4 times +1. So know that for every positive, there will be a negative factor. So my factors are 1, 2, and 4. And of q, it's just 1 and 2, obviously -1 and -2, but as I just said, we're not worrying about those. So 1 divided by 1, take every p divided by every q. 1 divided by 1 is 1, don't forget the plus minus. 1 divided by 2 is 1/2, don't forget the plus minus. All right, take your 2. 2 divided by 1 is 2. 2 divided by 2 is 1, which I already have. So I don't need to add more to my list. All right, then 4 divided by 1 is 4. And then 4 divided by 2 is 2, which I already have. Okay, so I'm going to show you the trick, right? Because that is 1, 2, 3, 4, 5, 6, 7, 8 possibilities. These are the possible ones. To find the actual ones, where you need to use the remainder theorem. Remember, the remainder theorem says if you plug those in and you get an output of 0, you know that it is a factor. But what I'm actually going to do is we're going to plug that equation into our graphing calculators. So here I just have y equals, so graphing calculator, I hit y equals, I type that sucker in, and then I hit graph. All right? So what you're going to do here is you're going to now hit trace, just that top second button in, hit trace. You can see it's kind of blinking because I'm touching it. So you hit trace, and then you're going to just try typing in a number. So I typed in a -1, I hit enter. And then if you look at the bottom of the white screen, it says when x is -1, the output is -51. So obviously -1 didn't work. And we can look there and see there's no x-intercept at -1 anyways. So I know that I'm going to need to try the positive values. So I'm going to hit trace again and try 1. It does not work, okay? I'm going to hit trace and try 0.5. It does work. If you look at the bottom of the right screen, it says the output was 0. So what does that tell me? It tells me that 1/2 is an actual value. Now, I already went through and tried all the others, and they don't work, but I'm supposed to have 3. So I'm going to tell you what happens when you get to this point. So I plugged all those into my calculator, I hit trace. I tried -1/2, it didn't work, it didn't give me a 0. I tried trace, I plugged in a 2, hit enter, did not give me a 0. So none of those work. So I can erase those because I don't need that list anymore. Clean this up a little bit. So I know that my actual root, I have a 1/2. Now the other two are probably irrational because if you remember, there were more x-intercepts. So I know they're not imaginary, but they probably are irrational. So they were not part of that rational. Notice it's only the rationals that this list will find. Rational root theorem, P's and Q's. But there are obviously more roots. So what we're going to do is we're going to try to get this to factored form using this actual root to kind of help us break it apart. So the first thing that we're going to do is we are going to take this root and put it back into the factor. Okay? Now, notice if I say x minus 1/2 equals 0, I can add 1/2 to both sides, and it is x equals 1/2, right? But there's another trick, because I don't really love dividing with fractions, is you can also multiply it by whatever the denominator is, and I'll get 2x minus 1 as I distribute that in, which also, if I solve, gives me 1/2, right? So just a trick to avoid fractions so that you don't have to use those when solving your problem, okay? So 2x minus 1 is the factor for the root x equals 1/2. So what I'm going to do is I'm going to divide that into the original polynomial. I'm going to divide it out because if we can divide something out, we'll find out what it multiplies by to create the original. So I like Bosk's method, so I'm going to do that. If you like long division, just do long division while I'm doing this. If you like synthetic, do synthetic division, except you can't do synthetic division because the a is not 1. So either long division or Box method. So I write 2x cubed right here because I know that I want to see what multiplied to create this. So I'm undoing Box method multiplication. So that means I had an x squared that multiplied to create 2x cubed. So I already accounted for the 2x cubed, but down here I get negative x squared. But I needed negative 25x squared, so that means I need negative 24 more x squareds. All right, so the negative 25 is now accounted for. Negative 1, negative 24, negative 25. Now I think, all right, so that must have been a negative 12x to create negative 24x squared, which means I get a positive 12x. But notice I didn't want 12x, I wanted 20x, which means I needed 8 more. And then 2 multiplied by something to create 8, that was a 4, okay? And then 4 times negative 1 is negative 4, which I wanted. So mission accomplished. The remainder is 0. It fit perfectly. So I know that 2x minus 1 multiplied by x squared minus 12x plus 4. So that's factored form. I can factor it a little bit more, but that's a good start to factored form. These two multiplied to create that polynomial, right? Okay, so here we have the root of 1/2, and here are 2 irrational roots. So notice we cannot factor x squared minus 12x plus 4. Try all day, you can't factor it. So you can either use the quadratic formula or complete the square, and I'm going to opt to complete the square to find those 2 factors. All right, so I'm now going to take this, complete the square. So when I complete the square, I'm going to get x squared minus 6x minus 6x, because I need to half that negative 12. Right, so to complete the square, it was x times x, which creates x squared, negative 6, which means completing the square, I should have got a 36. But notice, I don't have a 36 there, I have a 4. So I know that I needed a negative 32 to account for it. So I have 2x minus 1 times x minus 6 squared. But remember, x minus 6 squared created a 36, so I need that remainder of negative 32 to get that 4, okay? All right, so this is what I got going on, okay? These are my factors, but still this one's a little bit ugly, so we're going to work on that a little bit more. We're going to use the zero product property, set it equal to 0. Oh yeah, I already know that this is 1/2 because we found that out a long time ago. So 1 factor, x equals 1/2. Now the other one, x minus 6 squared minus 32 equals 0. I'm going to add 32 and then have x minus 6 squared equals 32. I'm going to take the square root of both sides. I'm going to get x minus 6 equals plus or minus root 32. I'll add 6 to both sides. So that means my 3 roots are x equals 1/2, x equals 6 plus or minus root 32. All right, so if I were to write it in complete factored form now, I'd have x minus 1/2, which can also be written as 2x minus 1, and I have x minus 6 plus root 32, and x minus 6 minus root 32. So factored form, solutions, I was looking for 3, I found all 3. All right, so fun, right? Okay, let's look at another one. So my job is to find the roots to solve this polynomial. I know that there will be 3 solutions, but I can't factor this, right? I don't have the skills to factor it. So first step, remember the rational root theorem. I'm going to list all the factors of p, which are 1 and 33. Remember, I'm ignoring the negative because negative 1 times 33 is a factor, but 1 times negative 33, so for every positive there will be a negative, and I'll just do the plus minus. So 1, 33, 3, and 11. And then factors of 1 are 1. So when I divide every p by every q, I'm just dividing every p by 1. So my possible rational roots are 1 and negative 1, 33 and negative 33, 3 and negative 3, positive 11 and negative 11. Now remember, the remainder theorem is really the idea behind this, is I'm plugging in all those numbers in for x and seeing which ones give me an output of 0, because I know that they will have a remainder of 0, which means that they are roots. They can become factors. Okay, but what I'm going to do is type this into the calculator, because that'll be way quicker than typing them all in. And shoot, I just forgot what it is. All right, so I have x cubed minus 2x squared plus 8x minus 33. And I hit graph. Oh, man. And I can see that there is only one x-intercept. And this one, I can change my window just to make sure, because remember 33 was 1, so I'll go out to, I'll go out to 34, and I'll go to negative 34 just to make sure. Yep, I can only see one x-intercept. Now I'm going to test it. I think it's 3, and if you look at the bottom of the white screen, the output was 0, so I know that 3 is the only actual root. The other 2 must be imaginary, because I'm not seeing them. So they're not real, they are imaginary. Alright, so remember, x minus 3 is the factor of that root. So we're going to divide it out so that we can find the other factors. So I like box method. If you like long division, go for it. So x cubed is the goal, which means I know that it had to multiply by x squared. Notice I did, and my x cubes accounted for, I did not want negative 3x squared, I wanted negative 2, so I need to do negative 3 plus 1x squared to get negative 2x squared. That means that I had an x there, because x times x is x squared, and negative 3x. But I wanted 8x, not negative 3x, so that means I'll need an 11x to account for the 8x. So 11 minus 3 is 8x, which means I had an 11 here. And of course it works out nice because the calculator, through the remainder theorem, I already knew that the remainder was going to be 0. Alright, so far my factors are x minus 3 times x squared plus x plus 11. There's my first solution, and the other two are there. So we know that this solution is 3, but we've got to do a little bit of work on that other one. Alright, so x squared plus x plus 11. Can't factor that. So I either need to use the quadratic formula or complete the square. I prefer to complete the square. So I'm going to have x squared, and then to get 1x, breaking it up perfectly, I need a half an x and a half an x. 1/2 plus 1/2 is 1x, which is what's in the center there. Okay, so that's x, that's x, that's a 1/2, that's a 1/2. And I know 1/2 times 1/2 is 1/4, but I don't want 1/4, I want 11, but I'm going to change 11 to the same denominator. 44 divided by 4 is 11. So I got 1/4, but I needed 44 fourths, which means I need 43 more fourths. That's my remainder for completing the square. Okay, so I have x minus 3 times x plus 1/2 squared plus 43 over 4. Alright, so far those are my factors. They multiply to create the original polynomial. I'm going to take this one though and set it equal to 0. Take the square root of both sides, which gives x plus 1/2 equal to, it's going to be imaginary because you can't take the square root of a negative, root 43 over square root of 4 is 2. Don't forget plus minus. Then I'm going to minus 1/2. So I have x equals negative 1/2 plus or minus an imaginary square root of 43 over 2. Alright, so there's 2 of my solutions. And the other one we found earlier, there's the third solution, and we're pretty golden there. Alright, so I just want to show you something real quick. Hopefully it'll be real quick. So that's what we're doing. We're finding the roots. We are factoring. Great. Okay. So I want to show you another one. 2x to the 4th minus x cubed minus 2x squared plus x equals 0. So I'm going to type that one into the calculator. Let's see. So I have 2x to the 4th minus x to the 3rd minus 2x squared plus x. And I'm going to hit graph. Alright, so this one's kind of tricky to see. So I'll zoom in a little bit. So notice on this one we can see all 4 factors. They're pretty visible there. I'm going to hit trace and check -1. Trace -1. I don't know why it's not working. Trace -1, and it works, okay? So I just checked -1. -1 is a solution. So when I go to the factor, I'm going to get x plus 1. So I'm going to divide that one out real quick. So those multiply. Here I have 2x cubed. I'm going to go kind of quick on this one. And that will give me, but I didn't want -3, so I'm going to put an x squared there, right? And everything's accounted for, came out kind of nice. All right? So notice, right now, I know that x plus 1 multiplies by 2x cubed minus 3x squared plus x. Now there is a GCF, but pretend that I still could not factor that guy, right? So I broke it down, but it's like, oh man, that's not a quadratic. I still can't factor it. Notice there is GCF, so you actually can factor this one, okay? All right, so notice, remember, I already knew that there were more, so let's check 1. So I hit trace, check 1. 1 was also an actual 0. So I also know that 1 is, which the factor of that is x minus 1. What we can do is we can keep dividing until we get down till it's manageable. But we already divided out from that original, so don't use the original. We're going to keep breaking this down. All right? So 2x cubed, 2x squared will create that. All right, and then, all right, so everything's accounted for. So now I know that x plus 1, x minus 1, and 2x squared minus x is the factored form. But notice on that last one, I can also pull out an x over here. GCF is x, so I have x times x plus 1 times x minus 1 times, I pulled out an x, 2x minus 1. Then I can use the zero product property, x equals 0, x equals -1, x equals 1, x equals 1/2 to find all 4 roots. So the point of this example was to show you, all right, if you find one root that works, divide it out. And if you can't factor, if there were more roots, keep dividing them out until you get to something that is manageable. All right, so write the polynomial with the given roots. So what if I give you the roots and tell you to write the polynomial? If you remember, we kind of went over this last unit. Notice, it'll just switch sign. But here's the weird thing about math, is mathematicians know that every imaginary and every irrational will come with a conjugate. Every imaginary and irrational comes with a conjugate. So if you have an x minus 3i, you have to have an x plus 3i. So don't forget that. We kind of talked about it before. All right, that's what we needed to go over today. Try those homework assignments. That's on Canvas. Good luck, and then email me if you have any questions.